Muy buenas tardes para todos. Es un gusto que nos acompañen hoy en esta importante evento para la universidad y para el capítulo estudiantil. Entonces, la metodología para la conferencia es la siguiente. Vamos a hacer la presentación en inglés y español. La conferencia a cargo del profesor David va a ser en inglés. Y al finalizar vamos a abrir un espacio de 10 a 15 minutos para preguntas y respuestas con el profesor David. Entonces, buenas tardes a todos y bienvenidos a los encuentros académicos del capítulo estudiantil del ACI de la Universidad Nacional de Colombia. Me presento, mi nombre es Edgar Nicolás Fuentes Alfonso, soy ingeniero agrícola e ingeniero civil de la Universidad Nacional de Colombia, sede Bogotá. Actualmente soy estudiante de la maestría en Ingeniería Estructuras en la modalidad de investigación en la misma universidad y soy el presidente del capítulo estudiantil del American Concrete Institute de la Universidad Nacional, la sede Bogotá. Hoy nos reunimos para analizar y valorar el papel de la ingeniería, la investigación, la innovación y el desarrollo en el campo de la tecnología del concreto. Nos complace contar con un invitado destacado quien compartirá sus conocimientos y experiencias en este magnífico espacio. El concreto como material estructural ha sido uno de los grandes protagonistas del desarrollo de la infraestructura a nivel mundial. Desde la patente del cemento Portland, registrada por Joseph Astin en 1824, pasando por la publicación del primer boletín de diseño de mezclas de concreto de la PCA, elaborado por el ilustre ingeniero Duff Abrams en 1919, hasta su aplicación en la construcción del edificio más alto del mundo, el Burj Khalifa, de 828 metros de altura, bajo la dirección del ingeniero Bill Baker, encontramos una valiosa contribución a lo largo del tiempo gracias a la investigación y el desarrollo en este campo. Tanto el ingeniero Abrams como el ingeniero Baker tienen algo en común: su formación académica y su prolífica labor investigativa en la Universidad de Illinois, institución de gran prestigio a nivel mundial en el ámbito de la tecnología del concreto. Por todo lo anterior, para mí es un honor presentar hoy al doctor David Lange, profesor emérito de la Universidad de Illinois y uno de los más reconocidos referentes actuales en la investigación sobre la tecnología del concreto a nivel mundial. Agradecemos su participación y les animamos a hacer preguntas y compartir sus inquietudes al final de cada conferencia. Esperemos que disfruten de este enriquecedor espacio de aprendizaje, que esta jornada sea fructífera y enriquecedora para todos los participantes. So, give me a second. Welcome remarks. Good afternoon, everyone, and welcome to the academic meeting of the ACI student chapter at the National University of Colombia. Let me introduce myself. My name is Edgar Nicolás Fuentes Alfonso. I am an agricultural engineer and civil engineer from the Universidad Nacional de Colombia, Bogotá campus. I am currently a research track master student in structural engineering at the same university. I also serve as the president of the American Concrete Institute student chapter at the National University. Today, we gather to reflect on and recognize the vital role of engineering research, innovation, and development in the field of concrete technology. We are pleased to welcome a distinguished guest who will share his knowledge and experience with us in this remarkable academic space. Concrete as a structural material has played a leading role in the development of infrastructure worldwide. From the patenting of Portland cement by Joseph Astin in 1924 to the publication of the first design of concrete mixtures bulletin by the PCI, written by the renowned engineer Duff Abrams in 1919, and its application in the construction of the world's tallest building, the 828-meter high Burj Khalifa, led by engineer Bill Baker, research and development in the field of concrete have made invaluable contributions through history. Abrams and Baker share something in common: their academic formation and extensive research work at the University of Illinois, a prestigious institution recognized worldwide for its contribution of concrete technology. For all these reasons, it is an honor for me to introduce Dr. David Lange, Emeritus Professor at the University of Illinois and one of today's foremost authorities in concrete technology research. We thank him for joining us, and we invite you all to ask questions and share your thoughts at the end of the lecture. We hope you enjoy this enriched learning experience. May this event be fruitful and inspiring for all participants. Ok, a continuación presentamos ante ustedes la conferencia titulada In Search of Eureka, The Joy of Discovery. Esta conferencia está a cargo del ingeniero David Lange. El ingeniero David Lange es profesor emérito de la Universidad de Illinois en Urbana, Champaing. Su investigación abarca diversos aspectos del comportamiento del concreto, incluyendo el desarrollo de la microestructura, propiedades en edades tempranas y durabilidad. Las aplicaciones de su trabajo incluyen construcción rápida, uso de materiales reciclados y reparación de infraestructura civil. Lange es ingeniero civil en la Universidad de Valparaíso en 1981. Tiene una maestría en Administración de Empresas en la Universidad de Wichita State University en 1984 y un doctorado en Ingeniería Civil en Northwestern University en 1991. Entre el 2005 y el 2020 fue director del Centro de Excelencia de Tecnología Aeroportuaria CIT, un centro de investigación financiado por la Administración Federal de Aviación y el programa de modernización OHIRE. Es miembro distinguido Fellow del American Concrete Institute y del American Ceramic Society. El Dr. Lange fue presidente del American Concrete Institute durante el periodo del 2018 al 2019. So, next, we are pleased to present the lecture titled In Search of Eureka, The Joy of Discovery. This lecture will be delivered by Engineer David Lange. David Lange is an emeritus professor from the University of Illinois at Urbana-Champaign. His research includes many aspects of concrete material behavior, including microstructure development, early age, properties, and durability. Application of his works include rapid construction, the use of recycled materials, and repair of civil infrastructure. Lange holds a BA in Civil Engineering Valparaiso University in 1981, an MBA in Wichita State University in 1984, and PhD in Civil Engineering Northwestern University in 1991. From 2005 to 2020, he served as the director of the Center of Excellence for Airport Technology, CEIT, a research center funded by the Federal Aviation Administration and the Ohio Modernization Program. He is a fellow of the American Concrete Institute and the American Ceramic Society. Dr. Lange served as president of the American Concrete Institute in 2018 to 2019. It is my pleasure to introduce Professor David Lange.
All right. Well, thank you for that kind introduction, Edgar. I appreciate that. And I appreciate the invitation to address the students today. Are we ready to start?
Yes.
Okay. Before I start, I want to kind of lay the groundwork for what I'm trying to accomplish here. You'll see that this is a broad sweeping talk about many different kinds of technology that has been used to characterize cements. But I know that I'm addressing a broad group. Some of you are researchers. Some of you are still young students. And so what I'm trying to do here, and I enjoy the chance to speak to this broad range, is to try to inspire a little bit of appreciation for what research is all about for our field. Not only are we trying to find new technologies that help serve our civil engineering construction and so forth, but we're also trying to see the contribution that research can provide to our own excitement about our profession, our own sense of purpose, our own sense of a contribution to society. All these things come through our work. And in research, that work is in this idea of the joy of discovery. And so the joy of discovery is my theme today, and that's what I'm going to talk about. What I have are a set of slides. I'm going to flip over to the slides now. And there, I think you can see it. If somehow things go wrong, Edgar's going to interrupt somehow. So our title for this talk is In Search of Eureka. Eureka! The Joy of Discovery. And there you have my contact information. So this idea of Eureka, where does that come from? I'm sure some of you recognize that. That's what Archimedes is told to have said. The story about Archimedes, to say Eureka, is this idea of discovery when he was challenged with a problem. You might remember the story. Archimedes was working with the king, who had given some gold to a craftsman and told this craftsman to make a crown of gold for him. But he had some suspicions. He thought maybe this craftsman had not used all the gold, but kept some of the gold for himself. So he contacted Archimedes and said, how can I tell if he used all the gold I gave him? I know how much I gave him, but I don't know how much has been being used here in the crown. And so Archimedes knew that the crown, I mean, we could weigh the total crown was the right weight, but we don't know what is in that crown. And so he knew that other metals could have been used that are less dense than gold. So he's reputed, the story goes that he went into a bath. He saw and observed the displacement of water when he came into the bath. And it was that moment where he said, I have found it, Eureka, because I have a clever way to measure the volume of an irregular shape. And by doing that and knowing the density of gold, I can tell if, in fact, all the gold was used that was given to the craftsman, the tradesman. And so the story goes that the craftsman, in fact, was being fraudulent, and he was punished, I guess we'll say. I don't know exactly how that story goes, what kind of punishment, but he was not being honest, and he was found out by this clever little idea that Archimedes had. So Eureka suggests the main idea here is progress is not linear. Progress comes in these moments, these Eureka moments where we advance the technology or in big spurts. And we had an example of that in sports. This is given. A TED Talk by David Epstein gave the example of how the record for the 100-meter freestyle has moved over the years. And you can see there are jumps. It's not just a straight line improvement through the years, but there are jumps where we get big impact of different kind of outside effects. So there is a change in the way the stroke was made in 1956. There was a change to the way the edging of pools was done in 1976 that reduced the turbulence in the turns. And there was a big effect of new swimming suit materials in 2008. And we could see the immediate impact of these technologies affected on the record in the world in the freestyle 100-meter. So we have all sort of had this moment in our own work where there is a brainstorm of a new idea that comes to us. And this is the idea of Eureka. Well, how have we done in the area of cements research over the years? I found it when I was cleaning out my office one day. I had inherited some old materials from my mentor, and there was a letter to the American Ceramic Society that had helped establish the cements division. This is not directly related to the American Concrete Institute, but it's a similar kind of an organization. So here this letter is from 1971 that said, what could this new organization, the Cements Division, be, could they work on? And they gave a list of the major fields we plan to study, which include 1, chemistry of anhydrous cement compounds, 2, chemistry of cement hydration, 3, microstructure of hardened cements, 4, fracture of hardened cements, 5, new cement containing composites. All of those things identified in 1971 remain important topics of research even today. So this is like, it's kind of amazing that somehow we don't solve these problems. These problems are continually improved over time. And these are some of the topics that you may have been working on in your own lab. Well, let me assure you that even though those topics are the same as 1971, yes, we have made progress, and we have experienced these kind of eureka moments where we get a jump step of improvement in our way of thinking. So I'm going to give you, to try to persuade you that Eureka is still alive and well in cements research, I'm going to revisit 5 of these areas that I have listed here and identify to you some of the things that I think are like, these are brilliant ideas. They really came along with a new step forward. And these are all in my lifetime, in the period of time I was active at the University of Illinois. So let's go ahead and take a look at these. Number 1, hydration modeling. This picture of hydration, of how hydration takes place and creates microstructure is dated 1948. T.C. Powers and T.L. Brownyard at early days of the Portland Cement Association. If you are working in the science of hydration, you need to know about these early papers of Powers and his team at PCA. He was the first to articulate this idea about how there are grains of cement in a field of water, and the water is an aqueous solution that changes its chemical composition over time as the material in the grains dissolves into the liquid phase. And then there are precipitation processes that bring those products back out into solid form that is new and different material than the original grains. And that creates a solid skeleton that we know as concrete. And these are some other pictures. Locker wrote a paper in 1976. This picture is in textbooks, and everybody refers to it. And it shows the same kind of grains and how the hydration product reaches out from the grains, kind of like spines, and they entangle each other and they start interfering with each other and gain rigidity between them. And that's how we get the stable skeleton in the final picture. And it also is how we have this characteristic of cement systems of porosity, meaning there's a residual openness to the structure. It's not 100% filled. There is a porous network. And that porous network is extremely important for the durability of Portland cement, because that's how we get transport of water. And water is involved in every kind of durability problem we have with concrete. So we knew that it was important to think about how this structure develops. And I'm going to use as my first example of a eureka moment where Klaus von Bruegel used computational tools to mimic, to model the development of a microstructure. And so he had his program software was called Hymostruck, and his thesis is 1991, but he did this work even far before that. But basically, he is tracking individual grains and how they grow and expand, and the volumes change with time. So it really takes a computer to keep track of these kind of volume changes. And likewise, Hamlin Jennings had another version of the model about how the grains were expanding spheres, and that hydration product would interfere. You see on the right side, there is an interference of volume, and that volume then has to be redistributed. So we get this incredibly complicated thing where we have expanding spheres, and the volumes have to be redistributed, and it changes the nature of the pore structure, and it changes the nature of the solid phase, and therefore products like or properties like the strength is changing as well. Okay, my favorite next step in this is the Eureka moment that came along at National Institute of Standards and Technology. Dale Bentz was in the middle of it. Ed Garbozzi was in this, and they created this microstructural model, a cellular microstructural model. They did so much work with this. This happened in the 1990s primarily. And there you see a reference. So if you are working in any area having to do with modeling microstructure, you need to be very familiar with the work that was done at NIST in the 90s. So here's a picture of sort of how it works. They started by now using the digital, every pixel of the image on the left is identified as having a phase. It could have, it could be C2S, C3S, C3A, C4AF. These are the common phases in Portland cement. And then, so on the right side, you see a picture with 5 sections. The unhydrated section, the tracing of edges in white, showing the pixels that need to possibly react. The reaction takes place, and they seed the liquid, the water phase with ions, and those float around in the model, touching other surfaces, propagating new products until you finally have a finished microstructure that you see in the far right. All the yellow is hydrated material, and we have a microstructure that looks strikingly like real life micrographs. Okay, so this is, I think, a good example of the Eureka joy of discovery of how to simulate microstructure. These images that were created with in the computer now are used in transport models, to validate transport models, to understand strength development, to understand stiffness of Portland cement. Many different kind of applications have been used for these digital models. Okay, Eureka case number 2, pore size measurement. Well, we were just talking about how microstructure develops, but now we can take the next step of looking at a specific part of it, pore structure. We have known for many years that the amount of porosity in Portland cement affects its strength, affects its water tightness, all sorts of things, impermeability, and hence durability. So how can we measure these micro, even nanoscale capillary pores that control strength and permeability? One of the good ideas that came along in the 90s was mercury intrusion porosimetry. The idea is kind of a clever one. And you can see it in the middle there, where you have a cartoon of the of mercury under pressure being asked to fill a volume of a pore. And so we have mercury under pressure. It's a hydrophobic material, so it doesn't want to flow into Portland cement pores, but we can force it under pressure. And you see on the right the curve of the amount of volume going into the sample. Let's see if this curve right here is the curve of volume with pressure. Pore diameter is the axis, but this could be thought of as pressure as well. So we're increasing the pressure. more and more and more. And there's some important threshold right about in here where we break through and we start filling the volume up. And so this characterization of pore volume is very important, and we can make a pore size distribution from this. Well, in our lab, we thought, well, this is fine. It's a nice experiment, but we can't see it. It's all inside a vessel. Mercury is a toxic material. We can't even touch this sample. So everything is done from the outside. How could we do this differently? And what we did instead was we replaced the mercury with Woods metal. Woods metal is also a liquid metal if you raise the temperature a little bit. So you raise the temperature to maybe 80 degrees C. 80 degrees C, the Woods metal is now liquid, and it can be used to flow into the pore structure under pressure. And then if you let it cool, it stays. If you let it cool under the pressure, it stays in the pores. And so we can get scanning electron microscopes of the microstructure filled with metal that became molten at a temperature less than a cup of coffee. But now that is cooled down, it's solid, and we can get these pictures. So what we have here is a picture at a low pressure, and then it goes up to E, a picture at a 10 times higher pressure, and we have essentially general penetration of our Woods metal into the microstructure. So this gives us a chance to get different images at 500,000, 1,500, 3,000, 5,000 psi using a fairly simple kind of a setup with a pressure and an autoclave for heating the Woods metal. By doing this, we can get a result that looks like this. Mercury intrusion shows the volume of pores at different sizes. So does the Woods metal. But what happens is that if we use a scanning electron microscope to look at these and physically measure the sizes, they're very different than the calculation by the physics of the intruded Woods metal. And so our insight here is that these pores inside the microstructure are considerably larger than we would have expected by the physics. And this helps us kind of relate the two kind of experiments to each other. So knowing about this, with this kind of information, we can design materials to have a different kind of a pore distribution where we have more smaller pores, less larger pores, and therefore stronger materials. And this, of course, was used by other researchers. And this is an example where some researchers at Delft use our approach to do both the pressurizing and depressurizing and measuring volumes so that we could see the progressive refinement of pore structure with age. At 1 day, 3 days, 7 days, 28 days, the size of the pores gets smaller and smaller, kind of doing a validation of our general understanding of cement hydration, how it densifies the microstructure. Okay, case number 3 for Eureka, fracture. When I came into my PhD, this was back in 1987, I came to Northwestern, and the practice there was that new students were given an opportunity to talk with the faculty and learn about different kind of research that was ongoing. Professor Suraru Shah was in the process of establishing what became known as the Center for Advanced Cement-Based Materials. Fracture was one of the main areas of work. Now, so why was this? Why was fracture a favored topic in about 1990? This was a period of time where the mechanics associated with fracture, so fracture mechanics, had made big leaps in steel material and metals, primarily out of World War II. There was a big growth of interest in the strength of steels for submarines and ships. And so there was a great advance in fracture mechanics. And some of our understanding is shown in these pictures here, where we have this idea of a crack tip and how there is a ductile zone around the tip of a crack. We call that a fracture process zone. And the theory was attractive to workers, researchers in concrete materials, because we too dealt with propagating cracks and we wanted to utilize some of the same mechanics. And so this is a picture from Hillerberg where there's a crack and then there's this thing called a cohesive zone. Up at the crack tip, you need some kind of an explanation to restrain the growth of the crack. If you did not have a cohesive zone, our material, if it were a brittle material, would simply extend that crack all the way across. There would be nothing to stop the crack. So we need in mechanics a certain explanation of why cracks are restrained, resisted. And so this was one of those kind of models. But when you start to see these models about the crack tip and this cohesive zone and the fracture process zone like this, now this leads you to think about fibers. If we can put fibers across a crack tip, this is one way we can restrain the growth of cracks and therefore get tougher behavior. We can consume energy in the fracture process. So these models were very instrumental at giving us the appreciation for how fibers were important for fracture, for the concrete materials. Well, we needed more tools. And immediately there were new kind of experimental techniques used to capture the strain, stress and strain of these materials. And one of them that had been underway when I arrived at Northwestern is this interferometry technique. And boy, oh boy, talk about difficult techniques. This is a very sensitive technique. This is with a special material. This is not concrete here, but with a photoelastic aggregate. And when you shine light through these photoelastic materials under stress, you can see these bands of in the image that represent areas of constant strain. So if you think about this, these shapes are under compression, as I show here, and the bands are areas of constant strain. So where are they straining the most? Right in points of contact, like in here, like in here. You see all these bands, and that's how we can start to understand and model what happens inside concrete and how cracking propagates in concrete. So, for example, one thing we know is the cracks tend to propagate along the boundary between aggregate and cement paste. Well, this partly explains that. You have all this strain that is occurring right at those connection points. And so it's not hard to think that this is where the crack is going to form, right down through here. So we have these new techniques and new experiments to see the strain and find cracking. And one of the things here is that you are able to make these maps of constant strain, 50, 100, 150. These are strain values. And you see these moments of discontinuity. And that is an open crack. So it's essentially a way to see cracks form even at very, very fine resolution. And it leads to improvements in materials, such as this use of fibers that I was mentioning. that we can use fibers in concrete. And this is a kind of a famous photograph here. This is a composite material to show that we can make bendable cement. And this came out in the 90s and was kind of a popular picture to show up in the media, trying to explain how we were going to be able to improve materials. Okay, case number 4 for Eureka, shrinkage. Shrinkage, of course, is a topic that has been studied for years. It's obviously a big problem with concrete materials. Pavements crack, buildings get cracks. And part of it is that the type of shrinkage we have in concrete is very complicated, very complex. Part of it comes from what's called chemical shrinkage. So when concrete goes through that chemical change we talked about at the beginning, there is a volume reduction of 6% or so when those products turn into those original Portland cement phases turn into hydration product. So even if you have a sealed sample, concrete will exhibit shrinkage. So normally we do shrinkage experiments like this, where we make a prism, we have a dial gauge, and we measure from end to end, and we can see the shrinkage of the sample. This is just to show you how many materials shrink, and we see these even in mud flats. Well, let's think of some better ways to measure it. And Eureka, we can do special cases by controlling our configuration. One of them is such as a dog bone sample, where we have a concrete sample in the shape of a dog bone. We can gather the ends or attach the ends to a testing machine, and then we can measure the length change. And as this dog bone wants to shrink linearly, we can see that with our measurement and apply a load with this hydraulic actuator and pull it back this way, thus compensating. By doing this, we can essentially see how much stress does the shrinkage of concrete create, because we can know how much we're having to pull back to get this back to its original length. And we also can more easily make a ring around a steel. This is steel in here. So the concrete goes in this area and the steel ring restrains it. And believe it or not, these strain gauges mounted on the inside of the concrete ring, the steel ring, will actually reflect the stresses caused by that shrinking concrete material. And then if it cracks, and say like in here, it goes crack, that breaks, all of a sudden these strain gauges will read 0. They all get relieved instantaneously when that crack occurs. So these devices are in the literature in the 90s and 2000s as different ways to understand residual stress, restrained shrinkage. Here was another special case where researchers at ETU in Denmark made a sealed sample that they could use for measuring lineal shrinkage. The interesting thing about this is that we can measure inside here. It's like a little accordion, so there's no the form is not participating in the experiment. It's just a closing and opening of an accordion. And autogenous shrinkage and chemical shrinkage stay together until here. When the set of the material, this is a very, very early material, so it's even fresh material. But at this point, the stiffened, hardened material stops shrinking. The chemical shrinkage continues. And this difference is going to result in stress. The stress that leads to early age cracking. So if you want to research, this is kind of a favorite paper, autogenous shrinkage in high performance cement paste, an evaluation of basic mechanisms. Pietro Lura, Jensen, Van Brugel wrote this great paper in cement and concrete research. There's the citation. So kind of puts that all together. So this area of research in shrinkage led to many different kind of offshoots of different kind of devices used to measure special cases. So I'm listing here new devices inspired in my group: early age shrinkage and creep interactions. Sala Altabot did his PhD in 2000 on early age, seeing how creep participated in relieving shrinkage stresses. Another key question was, because these are all three-dimensional problems, that they have a gradient. The outside surface is losing water to evaporation, but the inside is not losing the water at the same rate. So we have a change from the outside surface toward the center of the sample, and that creates a gradient that affects our shrinkage measurement and our stress. Chung-Jun Lee did some work on volume stability. Matt D'Ambrosia, controlling materials to reduce cracking in the field. Dan Castaneda had a paper on a field test for restrained shrinkage. Okay, my last case for Eureka is the 3D case. So 3D is nice, 2D is nice, is a scanning electron microscope image. But 3D is Eureka. How can we get from 2D and get up to 3D? And the answer is X-ray computed tomography. This is the best game in town for thinking about measuring microstructure in 3 dimensions at a microstructural level. I actually don't know, but I would think that your university probably has one of these kind of units, because see, first we saw these early experiments done at national laboratories. The synchrotron X-ray computed tomography, XCT, was first done at national labs, and individual universities did not have the equipment to do this until the field sort of developed these new machines. And Illinois was among some of the first to get a lab-based XCT. Smaller, affordable XCT equipment brings the capability into our own university laboratories. And so anyone working in microstructure characterization, where in the past you've relied so heavily on scanning electron microscopes to get images of microstructure, now we can get a 3-dimensional image, non-contact, by using XCT. So we can now observe hydration evolution in 3 dimensions. Here's the setup. There you see our lab-based instrument right here. Inside, you have a sample holder like this. And this is just an extension. This little teeny piece right here, this is our sample. And it's a small piece of cement that is very, very young. And it's going to undergo hydration in a moist environment. So we pull this out. The reason this is flat is because it's going to turn inside this machine, but we need it to be registered. So we need to know where it is in terms of its orientation. And now you can see over here our sample right there, and our X-ray source, and our lenses and our sensors over here. And now we're going to capture the image of this. What happens is that, let's see if I've got this. Yeah, I'm going to do it here. It's easy to imagine that this would be like an X-ray machine. You go to the doctor, you fell on the playground, you break your bone, your child breaks their bone on the playground, and you get what is essentially a shadowgram, where the X-rays pass through the child's hand. You see a shadow of the bone behind it, and you see whether or not there is a fracture of a bone, and then whatever action is needed to take place. That's fine. We can get one of those kind of images instantly here, but what we really want is 3D. How do we get 3D? We take one picture, we change the orientation by, let's say, 1 degree. We rotate it 1 degree, and we snap another image. We rotate it again by 1 degree, take another image, and do it again and again and again. We get 180 degrees pass through. So we have 180 images in our collection of images. We put this in the computer, and we say to the computer, give me a 3-dimensional image that solves all 180 individual pictures at the same time. In other words, tell me what 3-dimensional image could explain this set of 180 images. And therefore, you can go and get a 3-dimensional image like this. And so these are examples where we had samples made with a foil here on one side. I put this in gold in yellow color. We wanted to do this because of our interest in what's called the interfacial transition zone. So we wanted cement to be against a impermeable surface. And then over here, this is for 3 days. Now it's for 28 days. And what we could do is analyze the porosity as a function of distance away from the gold foil, and gives you a sense of the size and therefore the impact of the interfacial transition zone. These images here were some of this was basically our earliest experiment, where we measured fresh material against that gold. There's the gold in all these images at 1 day, 3 days, 7 days, 28 days down here. And this is the same area of microstructure. So if you look at it, you see similar kind of shapes, but there are some things to be learned by studying this. Look at this. That's a grain of cement. But look at it at 3 days, it's getting smaller. At 7 days, it shrunk quite a bit. At 28 days, it's gone. So this is the kind of evidence of hydration that we are very interested in. And it's not the same with every phase. So this is one particular kind of cement phase, and the others are different than this one. Look at this area. This is an area of original porosity. It's open. At 1 day, it's open. It fills up. At 28 days, it's solid. So we have the other example. Here we have, just to kind of complete my cases, we have a grain over here. By 28 days, it's still there. So we have some phases that are relatively inert and are not hydrating to create new product. So this is the basis of understanding lots of different things about the microstructure and how it develops. Another kind of interesting one is the development of a porous zone. You see down here that did not exist in the earlier stages. Okay, so there's lots of things to study here in these time studies of hydration, cement hydration with X-ray CT. there's some more cases to look at. Okay, so these kind of images now can be used as a study of a transport of water moving through this microstructure. And so we had a paper working with partners at Delft University where we were using hydration models and pore structure and kind of bringing together our knowledge of the pore size distribution, the diffusivity of liquid species through the microstructure, and seeing if our microstructure matches up to other kind of experimental results. Okay, so there you have 5 different examples of where research has experienced this kind of eureka moment, where in my career at Illinois, we've had this nice and surprising result where we say, yes, now we understand the problem in a new and different way. And because of that, we can make new steps in developing materials. So how do we institutionalize Eureka? That is, how can we capture Eureka and make it part of our everyday experience? So we want to have this experience of discovery. I want you as students to feel excited by the process of learning new things, of doing things in the lab, of discovery, and not do that. Not do this. So this is a kind of another way of looking at your ambition of life. And here this student is at the beginning of his graduate studies thinks he's going to win a Nobel Prize. And by the end of his graduate studies, he's just satisfied with, I hope they have pepperoni pizza. Some of his aspirations are going down. So we don't really want that to happen, but it's kind of a funny idea about how our ambitions change with time. So some problems are timeless. Definitely have seen some of those today. Every new generation of researchers and students revisit some of these ideas with new technology, and therefore greater computing power and greater benefit of using the literature, the history. And so I'm assured that Eureka will be heard in the future, and hopefully by yourself, where we make this advance, but then leap to a new level based on these findings. Okay, a closing remark. As you heard at the beginning, I had the opportunity to spend a couple of years as president of ACI. And in that year, I took time to go back and read some early things. And there was a president, Mr. Blanks, what was the date of this? 1949. Yeah, April 1949. And he was asked to comment on the future of concrete. And so he said the following, which is, I hope, some instruction for all of us. When shall we take concrete from the specialists, that is, the microscopists, ambitious scientists, and chemists, and give it back to engineer? I see the answer very clearly. The answer is never. That's interesting. That breed of engineer, the pick and shovel, transient level type, has become an extinct species of animal. Think about that. It means that even at this early point, it was clear to the president of ACI that the amount of input we need from our academic side, the people who think kind of philosophically and with research on their mind about materials, are very much needed to move forward our field. We don't need people just to run ASTM tests and just to do simple things. We need people with a good mind and the training that you're getting at the university to think about all the issues related to materials and bring about a better, more complete solution for construction in the field. Needs real partnership. He's talking about a strong and lasting and effective partnership between researchers and the construction trade. Okay, so that brings me to the end, and I think I'm now showing there. So I'm now happy to take questions from anyone, and Edgar, it's back to you.
Yes, Professor David, thank you very much for this great and grateful lecture. Is to honor to the chapter and the university. And now, this is a comment with Jose Luis Chacon. This lecture is very good, uh, and many things Jose Luis don't know about the concrete technology. So it's a very good lecture.
Well, I
And
hope that you all had a chance to see something that was new to you and maybe a bit provocative to open your eyes and stretch your thinking about properties of concrete.
yes, doctor. And I prepared for you two questions about the
Okay.
lecture, and I'm going to read for you. The first is, in your opinion, what is the most promising innovation in concrete technology that could significantly reduce the environmental impact in the coming decades?
Okay. So let's see if you can repeat that for me. So you said, what's the most important technology for reducing environmental problems?
Yes.
Okay. Well, I'll tell you that there's been a lot of attention for new binder chemistries. Portland cement is not a new chemistry. Portland cements is over 100 years, about 200 probably years old in the basic chemistry. But what you see right now is a lot of people have interest in new chemical admixtures, different kind of powders that can be added during the mixing process. So there's basically an opportunity here to use waste materials. How can we use ash materials from combustion to react with Portland cement, creating a better Portland cement and getting rid of waste at the same time? So those are the things I'm most okay. This gives me a chance to say a few more things. This is the most important thrust of how industry needs to attack the environmental concerns, using waste ashes and creating improved concrete at the same time. I think this is more important than paying more attention. I mean, we have a lot of people paying attention to CO2 issues. I'm a little less enthusiastic about worrying about that, because every time I hear of new ideas in that area, they compromise sometimes the properties and performance of the cement and the cement and concrete. What we want to do is make a better material and improve the concrete at the same time. If you have to take a step back from performance to say that you've improved the green reduce the CO2 emissions, I'm less interested in that. It's not, because our first goal as engineers is to make a very, very good, long-lasting material. The best way to be environmentally conscious is to make a durable concrete. If we can make the concrete last 100 years, we win. I don't really care about CO2. If we make this stuff last 100 years, we win. And so the durability challenge is probably the most important challenge to me.
Okay, thank you, Professor. Now, a question by Ariana Ortiz. Uh, does it involve any study on polymers and its relation to cracking or performance with cement as aggregate?
There's very interesting things going on with polymers. Let me just point as an example, the whole area of repair materials. We have a lot of technology going on where repair materials are being improved, intrusion of epoxies to improve the microstructure, and the use of non-metallic building materials. It's ACI has created a center of excellence on non-metallic building materials to be used in concrete. So we are embracing FRP bars, for example. And that's basically taking the best things about polymers and getting them to play a role in concrete technology and concrete buildings. I think that there's a lot of excitement about FRP bars in areas along the seashore where we have high salts and corrosion is a big problem. If we can get rid of steel, we can get rid of a big concern. So if you're interested in FRP bars and all the things going on there, I would point you toward ACI's Center of Excellence for Non-Metallic Building Materials. They've done a lot of homework on that. There's things going on, conferences going on, sessions at ACI are featuring that. So,
okay, thank you, Dr. David. And I'm going to talk about this question and how can engineers balance the demand for durability and performance in concrete structures with the need to lower carbon emission and promote sustainability?
Well, I kind of led into my answer on that. Carbon emissions and sustainability seem to me to be a secondary concern. I realize that not everyone would say it the way I just did. I just think that our first goal as engineers is to make a good, durable material with great properties. And if we find ways to also keep our emissions down, that's fine. But I don't think of that as our biggest problem. I think we want to keep our eye on a good durability.
Okay, Professor.
After all, what's better for the environment than to use the same building again and again and again without even moving it? I mean, just different lifetimes. If I can get 100 years, I've had three lifetimes of the material right there.
Yes, I think so. And this is a comment for Natalia Roman. Amazing presentation. It was very interesting. And
Thank you.
I have another question. In the alkali silica reaction, in your experience, something, the history of the concrete technology, what is this moment Eureka for alkali silica reaction?
Well, hopefully some of these problems are kind of getting solved. I maybe not completely in the right spot here, but let me give you the example with Illinois. Illinois had problems with freeze-thaw problems with aggregate and alkali silica reactions with aggregate. The Illinois Department of Transportation 20, 30 years ago began a big testing program to look at all the aggregate sources that were used for Illinois DOT projects. And they graded these. And they took source one. Are you okay on freeze thaw? Are you okay on alkali silica reaction? All these kind of things. And they had to pass certain thresholds. Source two, you're okay. Source three, you're okay. For source four, you're not doing so well. We're going to actually prohibit you from being used in Illinois. And so they turned the testing program into a quality assurance tool to make sure that the contractors in Illinois had the ability to reject poor performing aggregate. That's where we should be going, that we need to be defenders of infrastructure and defenders of quality. And we have this great knowledge about alkali silica reaction, ASR, freeze thaw, all these other durability problems. Let's go ahead and apply them in the field to get good quality aggregate into our buildings and roads. So I think that some of these areas have made tremendous progress. So now it's time to implement.
Okay, thank you, Dr. David. And one no question mark, like a massage for the future civil engineers and young engineers of
Well,
the.
if you want me to, I'll summarize my talk today. I want everyone listening to feel excited and dedicated to their studies so that they realize that you're in the process of preparing yourself to contribute to society, to make advances, to create a great infrastructure. That's your goal. That's your honorary duty as an engineer. And this can lead satisfaction in your job, a good self-esteem about what you're doing, and even profitability in your own life and your family. So keep your eye on serving your fellow man, and good things will come from that through civil engineering structures.
Okay, thank you, Professor David. For me, it's a great honor, and with this message, we're going to end the lecture. Now, I'm gonna to closing remarks. A special thank you, Dr. David Lange, for this time and dedication to this event at Universidad Nacional de Colombia. Has been a remarkable experience for both the ACE student chapter and our university. We also extend our sincere thanks to everyone who joined us today and to all those who supported the promotion of this event, the professors from the structural engineer area of the civil engineer program, the graduate program in structural engineer, the members of the ACE student chapter, the civil engineer academic coordination office, and the faculty of engineering and the National University of Colombia. We are also grateful to the Colombian chapter of the ACE and the Colombian Association of Earthquake Engineers, AIS, for their help and promoting the event. Please remember to subscribe to our YouTube channel, ACE Student Chapter, and the channel of the faculty. Thank you very much, and we wish you all a pleasant afternoon. So, con esta última pregunta, finalizamos el evento. Entonces, quiero dar unas especiales gracias al profesor David Lange por su tiempo y especial dedicación a este evento en la Universidad Nacional, una experiencia grandiosa para el capítulo y para la universidad. Agradecimiento especial a quienes nos acompañaron en el día de hoy y a todas las personas que nos apoyaron en la difusión del evento, a los profesores de la línea de estructuras del programa Ingeniería Civil, al posgrado en estructuras, a los integrantes del capítulo estudiantil, a la dirección del área curricular de Ingeniería Civil y a la Facultad de Ingeniería de la Universidad Nacional de Colombia. También un agradecimiento a la seccional colombiana del ACI y a la Asociación Colombiana de Ingeniería Sísmica AIS por la difusión del evento. Recuerden suscribirse a nuestro canal de YouTube, Capítulo Estudiantil ACI UNAL, al canal de la Facultad, FIBOC UNAL. Muchas gracias y feliz tarde para todos y todas.